Space, the final frontier. These are the voyages of the starship Enterprise. Its 5-year mission, to explore strange new worlds.
Sorry, no space missions today. We're going to be talking about a very interesting phenomenon called pulsars. Pulsars are neutron stars that emit beams of electromagnetic radiation in Earth's line of sight. Like black holes, they are endpoints to stellar evolution. As shown in the diagram, stars begin as stellar nebulae, which are clouds of dust, hydrogen, helium, and other ionized gases. Neutron stars and pulsars originate from massive stars, forming after the star undergoes a supernova. Average stars, on the other hand, form white dwarfs, which are alternate endpoints to stellar evolution. PSR J0108-1431 is the closest known pulsar to the Earth. It lies in the direction of the constellation Cetus, at a distance of about 85 parsecs or 280 light-years from our planet. The pulsar is closest to the star Mira, or Omicron Ceti. This pulsar was discovered in 1994 during the Parkes Southern Pulsar Survey at the European Southern Observatory in northern Chile with the Very Large Telescope. And yes, that is the telescope's actual name. It is considered a very old pulsar with an estimated age of 166 million years and a rotation period of 0.8 seconds. As of 2008, it is the second faintest known pulsar. No companions have been discovered in orbit around this object. Because pulsars are observed by radio telescopes that detect the radio emission from these objects, people often think that astronomers listen to the pulsars rather than detect their light curves. A light curve is a plot of how the brightness of an object changes as a function of time. Although astronomers do not listen to pulsars, some astronomers have taken light curves from a sample of pulsars and converted them to sound, so you can hear the difference in their rotation rates. Eventually, Subramanian Chandrasekhar, an Indian-American astrophysicist, developed the Chandrasekhar limit, which says that the mass of a white dwarf cannot exceed 1.44 times the mass of the Sun. The following clip is an animation developed by Chandrasekhar that shows the pulsars in X-rays. The following clip is of light curves taken by astronomers from PSR J0835-4510, also known as the Vela pulsar, and converted into sound. Pulsars were first discovered around 1910. When Sirius B, a white dwarf star, was shown to have a mass similar to our Sun. From its known distance and luminosity, it was clear that the star must be incredibly and, as it seemed at the time, impossibly dense. Although scientists then did not realize it was a pulsar, this was the first known observation of one. In 1931, Chandrasekhar showed that there is a limiting mass that no white dwarf star can exceed, which is around 1.4 solar masses. In 1932, Chadwick discovered the neutron, and only a few years later, in 1934, Bod and Zwicky showed that the contraction of a 1.4 solar mass object would only be halted by the internal pressure exerted by a degenerate neutron gas. They termed the resulting stable star a neutron star, and suggested that such stars would be formed during supernovae. At the time, neutron stars were thought to be too faint to be detectable. Pacini and Gold, in 1967 and 1968 respectively, described how the neutron star would have a radius of approximately 10 kilometers and a surface magnetic field strength of about 1012 Gauss. It was noted that if the star were spinning, then the electromagnetic waves would be emitted because of the strong magnetic fields. Pulsars were actually discovered by accident in July of 1967 when Jocelyn Bell, a graduate student in astronomy, worked with her advisor Anthony Hewish to investigate a strange anomaly in the data from the radio telescope. The telescope was supposed to recognize scintillating sources and interferences, but the data showed a signal that did not quite look like a scintillating source or man-made interference, and Bell quickly realized it was a signal consistently coming from the same patch of sky. Initially, they managed to rule out extraterrestrial life, human interference, and other stars. From July to December of 1967, more irregularity in the data occurred, and by the end of January, Bell and Hewish submitted a paper to Nature describing the first pulsar. Nature magazine, that is. In February, a few days before the paper was published, Hewish gave a seminar in Cambridge to announce the discovery. Because the source of the pulsar was not determined at the time, the press thought this was a possible finding of extraterrestrial life. Additionally, other astronomers were also excited about the finding and joined in a race to discover more pulsars and find out what these strange sources were. By the end of 1968, dozens of pulsars had been detected. Thomas Gold detected that pulsars are actually rapidly rotating neutron stars. Neutron stars were actually predicted in 1933, but were not detected until the discovery of pulsars. The density of the star determines the pulsation period, or how much time there is between electromagnetic pulses. Denser stars pulsate more quickly than low-density variable stars, whose brightness as seen from the Earth fluctuates. However, normal stars and white dwarfs are not dense enough to pulsate at rates of under 1 second. Neutron stars would pulsate too quickly because of their huge density, so pulsars must pulsate in a different way than normal variable stars. Normal variable stars and white dwarfs cannot rotate fast enough to emit electromagnetic radiation because they do not have enough gravity to keep themselves together. They would spin themselves apart. Neutron stars are compact enough and strong enough to rotate that fast without destroying themselves in the process. As stars collapse, their rotational inertia decreases dramatically, but the angular momentum is conserved before and after the collapse. This results in a larger angular velocity, thus giving the newly collapsed star a high rotational kinetic energy. These neutron stars are spinning incredibly fast. The gigantic stars from which they formed would have had rotational periods similar to that of our Sun, which revolves about once every 27 days. But these stars have now collapsed into an incredibly dense object only 30 kilometers across. When a rotating mass is moved closer to its center of rotation, the speed of rotation has to speed up to maintain a quantity called angular momentum. A star that rotated once a month can end up rotating once per second after its collapse into a neutron star.
Pulsars are highly magnetized stars. Their beams of radiation are emitted along the magnetic axis of the pulsar, which spins along with the rotation of the star. The magnetic axis determines the direction of the electromagnetic beam, and it might not be the same as the rotational axis. The misalignment between the rotational axis and the magnetic axis causes the beam to be seen once for every rotation of the neutron star, which leads to the pulsed nature of its appearance. And now for some questions about pulsars.
Pulsars also aid in experiments involving the nature of gravity and have been incredibly useful. For example, in timing the period of each pulse, astronomers can determine the properties of the neutron stars. One conclusion that has been established is that pulsars' motions are not dependent on their structure. Due to their extremely precise periods, pulsars are also used as astronomical space clocks. pulsar timing is more accurate than atomic clocks. Known pulsars have rates ranging from a few milliseconds to several seconds, depending on the speed of the star's rotation. Slight, regular variations in the timing of the pulses indicate that the pulsar is moving back and forth, orbiting the center of mass of a system with one or more planets. Astronomers can deduce the orbit as well as the mass of these planets by precisely measuring irregularities in the timing of the pulsars. The method is so sensitive that it can detect planets as small as 1/10 the mass of the Earth. The pulsar timing method was used in 1992 by Alexander Wolszczan and Dale Frail to detect the first confirmed exoplanets. These exoplanets orbited a pulsar, and as of October 2012, 15 similar exoplanets have been discovered by this method. A pulsar timing array, or PTA, is a set of pulsars which is analyzed to search for correlated signatures in the pulse arrival times. The most well-known use is to use an array of millisecond pulsars to detect and analyze gravitational waves. Millisecond pulsars are used because they appear not to be prone to the star quakes and accretion events which can affect the period of classical pulsars. Globally, there are 3 active pulsar timing array projects. These 3 projects have begun collaborating under the title of the International Pulsar Timing Array Project. These 3 include the Parkes Pulsar Timing Array at the Parkes Radio Telescope, which has been collecting data since March 2005. The European Pulsar Timing Array, which uses data from the 4 largest radio telescopes in Europe. The Lovell Telescope, the Westerbrook Synthesis Radio Telescope, Effelsberg Telescope, the Nankai Radio Telescope, and the Sardinia Radio Telescope, and the North American Nanohertz Observatory for Gravitational Waves, which uses data collected by the Acreebo and Green Bank radio telescopes. There are approximately 30 pulsars total involved in the International Pulsar Timing Array.
Thanks for listening. You're a star.